So here uh, left hand plane pole gives minus 20 dB per decade roll off in magnitude. Okay, and phase shift due to left hand plane pole is minus 90 degree. So there is a degradation of phase by minus 90 degree, and at omega p phase will be degraded by minus 45 degree. Okay, now let's see now we will see second. So this is first. Now second we will see left hand plane 0. So in case of left hand, so 1 plus s by say omega z. So this is the transfer function. So magnitude is given by square root 1 plus omega by omega z square, and phase is given by tan inverse imaginary part upon real part, which is equals to tan inverse omega by omega z. Okay, so in this case if we draw Bode plot, so magnitude response, phase response, this is omega axis, say this is our here. Okay, I should draw it like this, omega z. Here I should draw it like this, say this is okay. Now this is omega z. Now in this case there is a increase in phase or magnitude by 20 dB per decade, plus 20 dB per decade. Okay, now so this is tan omega z, this is say 0.1 omega z. Now in this case phase is increased by phase is increased by 90 degree, and at omega z phase is 45 degree. Okay, so there is phase will increase. It is in phase term it is opposite of left hand plane, and in magnitude it is also opposite left hand plane pole. Okay, now let's see third one, Bode plot for right hand plane 0. So hs 1 minus s by omega say z. So magnitude is given by square root of 1 by omega upon omega p square, and see here omega term is at numerator, here also omega term is numerator, so phase is, as frequency increasing, phase is increasing. Here omega term is in denominator, so as omega increasing magnitude is should reduce. Okay, now phase response is again tan inverse imaginary part upon real part, so tan inverse, so minus omega upon omega z by 1 equals to minus tan inverse omega by omega z. So here this negative sign shows that phase response is like left hand pole, so it will be like this. So and magnitude response is like left hand plane 0. So is plus 20 dB per decade. This is magnitude, this is phase, and this is 0.1 omega z, 10 omega z, omega z. So 0, this is 90 degree, and this is 45 degree. Okay, so this magnitude response is also similar to left hand plane 0, and this is similar to left hand plane pole. Okay, phase plot is similar to left hand plane pole. Now let's see our fourth. So that is right hand plane pole. So it is given by 1 by 1 minus s by omega p. Okay, so now in this case magnitude is given by 1 by 1 plus omega upon omega p square. So it means as frequency increasing, magnitude reduces. Now let's see phase response. Phase response. Phase response, we need to find out phase response. So Hs we will which is equals to, okay, tangent inverse imaginary part upon real part. Now this is in denominator, we need to make it in numerator for finding imaginary and real part. 1 minus j omega upon omega p. So multiply 1 by j omega upon omega p, 1 plus j omega upon omega p. So it will be 1 plus j omega upon omega p. So 1 plus so this will be omega upon omega p square. So phase is tan inverse omega upon omega p. Okay, now so this is positive one, so we draw this. Now here minus 20 dB per decade. Okay, and phase will be, this is say omega p, this is 10 cross omega p, this is 0.1 omega p. So phase roll-off actually start at 1/10 of pole frequency or zero frequency, or it will keep changing and till 10 times 10 cross of pole or zero frequency. So here in this case it will be like this. So and each pole and zero gives phase change of 90 degree. It can be positive or negative depending upon whether it is left hand or right hand plane pole or zero. Okay, so this is magnitude, this is phase, and this is omega. Okay, so we have seen pole and zero response, Bode plot response. Now we will see single pole system, gain bandwidth product, and Bode plot for single pole system. We have already seen, but just we reviewed that thing, and we will see that thing. Then we'll go with common source, common gate, common drain, differential amplifier, AC response, or Bode plot we will see. Okay, thank you.